Hello, my name is Brian Plummer and this is the first video I have produced on the subject of C programming. The topic I have chosen relates to the situation where we are working with integer variables and have the need to multiply an integer variable with a fractional value to produce a result that is the nearest integer value to the real result. For instance, if we need to plot a diagonal line on a graphic display from the origin to the point 1400, we can create a loop and step through the x-coordinates from 0 to 1000 and calculate the y-coordinate for each value of x, and then plot each xy point on the display. Now, because we are dealing with integer values, the plotted line, which may look straight from a distance, will actually consist of small horizontal lines of either 2 or 3 pixels each. Although the formula for calculating the y-coordinate is simple, you do need to think about how you implement it within the C language. If you create an expression like this, it would probably fail, because if the variables are of type int, then the intermediate calculation of x times 400 would eventually cause an overflow. If the constant were enclosed in brackets, again this would not work, because 400 over 1000 would be performed as an integer division and give a value of 0. What you could do is simplify the fraction like this, and it would be performed using integer arithmetic. Or you could enclose the fraction in brackets with one of the fraction values entered as a type float. In this case, the compiler would evaluate the expression as a floating point multiplication, which is about 17 times slower than the integer calculation. In both cases, the integer value assigned to y would be rounded down and would not be the nearest integer value to the real result. The objective of this tutorial is to develop a macro that will perform this operation using integer arithmetic and round the result to the nearest integer. When a CPU executes a program that calls for a floating point operation that is not supported by a hardware floating point unit, the CPU performs the floating point operations in software using functions from a floating point library, and this is significantly slower than using an FPU. Floating point operations without the support of an FPU require considerably more processor resource than integer operations, so it may be beneficial to use integer arithmetic operations in situations where processing speed is a primary requirement. The information within this tutorial relates specifically to the Microchip XC16 compiler used with the 16-bit PIC24 microcontroller, which does not contain an FPU, but the information is applicable to other types of CPU that do not have the support of an FPU. The C language supports both floating point and integer type arithmetic operations. The operation type used by the compiler for each operation within an expression is dependent upon the types of the two operands associated with an operator. If one or both operands are floating points, the operation is performed as floating points, giving a floating point result. Whereas if both operands are integers, an integer operation is performed giving an integer result. Starting with the basics, let us consider a simple formula for multiplying a variable with the constant pi. In this example, the float value contained in variable v is multiplied with the literal constant using a floating point multiplication operation, and the result is assigned to floating point variable a. Here the input v and output a are integer variables, but the multiplication and addition operations are floating points. The integer value contained in variable v is converted to a floating point value to match the type of the literal constant, and then multiplied with the constant using floating point multiplication. In order to round the result to the nearest integer, we must increase the absolute value of the float result by 0.5. The result is then automatically converted to an integer before being assigned to the integer variable a. In the C language, when a floating point number is assigned to an integer variable, it is accomplished by truncating the value after the decimal point, which effectively rounds the result towards 0. This means that positive values are rounded downwards and negative values are rounded upwards. In order to produce an integer value that is the nearest to the real number, it is necessary to increase the absolute value of the floating point value by 0.5. Here it is assumed variable v can be set to a positive or negative value. The absolute value of the product is increased by 0.5 to produce the nearest integer value. The conditional operator is used to determine the sign of the value in variable v, and then either add or subtract the literal constant value of 0.5. The floating point result is automatically converted to a type int integer to match the type of variable a, and the value assigned to it will be the nearest integer to the real value. This example is the same as before, except that instead of using a literal value for pi, it has been replaced with a symbolic constant. The compiler preprocessor will perform a string replacement and replace the symbol pi with its defined value, and this takes place before program compilation takes place. This example is a simple and straightforward way of doing the computation, and perfectly adequate for situations where the processing time is of no real consequence. But if we are performing this calculation within a time-critical loop, we may need to avoid the slow floating point operations and also the conversions between variable types int and float. We will now consider the use of integer arithmetic to perform the same calculation, and for this we will require the representation of pi as a fraction using integer values instead of a floating point number. The value of pi is an irrational number, which means there is no fraction that can fully represent its value, but there are several well-known fractions available with varying levels of accuracy. So if we first consider the fraction 22/7 to represent pi, the first thing to note is that we are replacing a floating point multiplication with an integer multiplication and an integer division, because a fraction is effectively a divide operation. Mathematically, multiplication and division have equal order of precedence during evaluation. An arithmetic calculation produces the same result whether the multiplication is performed before the division or vice versa, but this is not the case when using integer operations, because integer division discards any remainder. In order to keep the integer rounding error to a minimum, the expression should be arranged such that the division operation is the last operation to be performed. When C performs an integer division operation, the result is rounded towards 0, and this applies to both positive and negative values. To round a divide expression result to the nearest integer value, the absolute value of the dividend must be increased by half the divisor value. In other words, it must be added to a positive dividend and subtracted from a negative dividend. This is similar to the decimal rounding mentioned earlier. Returning to our example program, we now have pi defined as the fraction 22/7. Now that all the values within the expression are integers, the divide operation will be performed as an integer division, and it is the last operation to be performed within the expression. The inclusion of an integer rounding term of half pi 2 ensures the result is rounded to the nearest integer. The conditional operator is used to determine if the value in variable v is negative, and if so, we'll change the sign of the rounding element by multiplying with -1. The representation of pi as 22/7 is only accurate to 3 decimal places, so if we require greater accuracy, we need to represent pi with a larger fraction. Here we are representing pi as 355/113, which is accurate to 6 decimal places, but it has introduced us to the next potential problem area relating to variable overflow. A type long cast has been inserted in front of variable v to prevent the intermediate calculation from overflowing. The typecast operator changes the value read from variable v from a 16-bit type int integer to a 32-bit type long integer. All the operations will now be performed as type long, with the result automatically demoted back to a type int when assigned to variable a. So we have seen that by representing the constant as a fraction using integer values instead of a decimal floating point value, the compiler will create code that performs the calculation using integer operations. What we will do now is create an expression that can contain a floating point constant and convert it to an integer fraction within the expression. We can multiply the expression with n over n without changing the result, because n over n is equal to 1. The value n must be a positive integer literal constant, but we won't worry about its value at present. We now need to modify this so that it can be used in a C expression that uses integer arithmetic operations. The evaluation order is changed so that the division is the last operation performed. Enclosing c times n in brackets ensures it will be calculated during compilation and not at runtime. This is because both the constant c and n are literal constants. As the constant c is a floating point value, the expression c times n will produce a floating point result. This is converted into the nearest integer value by increasing the absolute value by 0.5 and then applying a type long integer cast. The result of the integer division by n is rounded to the nearest integer value by increasing the absolute value of the dividend by half the value of the divisor. The sign of the rounding terms 0.5 and n over 2 can be determined using the conditional operator. So we now have an expression which can contain a floating point constant with the runtime calculation performed using integer operations. Generally speaking, the larger the value of n, the greater the accuracy of the result. But if n is made too large, an overflow in the intermediate result can occur. In this example, n has been given the value of 100,000. So we now have a way of performing the calculation using integer arithmetic, and by ensuring that the intermediate results of the calculation are of type long integers, we have avoided variable overflow occurring. The use of type long integers introduces us to yet another problem. Our overall aim was to avoid the poor performing floating point operations and use instead the much faster integer operations. However, type long integer division does require a lot of processing power and has an execution speed similar to floating point operations. But there is an exception to this speed penalty, and that is when the divisor is a literal constant with a value equal to a power of 2. This is because the compiler performs the divide operation using a binary shift right operation, which is very fast. So here we have made n equal to 2 to the power of 16, which is 65,536. Instead of using a divide operator where the compiler would perform the operation using shift right, we can replace the divide operator with a shift right operator. And by doing so we can also remove the sign test from the integer rounding item so that it is always added to the numerator. The reason for this is that there is a subtle difference between the divide and the shift right operators. Although they will produce the same result when the numerator is positive, this is not the case when the numerator is a negative value. This is because the integer divide operation rounds the result towards 0, whereas the shift right operator rounds the result down, so that positive values round towards 0 and negative values round away from 0. So if we want the result to be rounded to the nearest integer, then with the divide operation we had to increase the absolute value of the numerator by half the denominator value. Whereas with the shift right operator we always add half the denominator to the numerator value. So if we replace the integer division with a shift right operator within our generic expression, it becomes unnecessary to determine the sign of the expression v times c, because we always add half the denominator value to the numerator, regardless of the sign of the expression v times c. By enclosing the constant c in brackets with a floating point typecast increases the flexibility of the expression. The constant c can now be defined as an integer fraction as well as floating point. Also, the accuracy of the product c times 65,536 can be increased by using a type long double floating point cast. So we now have an expression where the compiler converts a given floating point constant into an integer fraction with a denominator value of 2 to the power of 16, and then generates runtime machine code that will perform the calculation using integer arithmetic. And this is considerably faster than using floating point arithmetic. It should be noted that the sub-expression shown in red is calculated by the compiler during compilation of the program. This is because the operands are all literal constants. So although the expression contains floating point operations, they are not performed at runtime. The compiler generates runtime machine code that will perform the integer operations shown in green. Using this expression within a program would be rather cumbersome, and when viewed in the listing it would not be immediately obvious that all it was doing is multiplying v times c. We can improve this situation by defining the expression within a macro. Shown here is the definition of a macro that accepts two parameters for the variable and the constant. This considerably improves the usability of the expression and can be used anywhere that requires the calculation v times c, where v is an integer variable and c is a literal or symbolic constant, and the result is the nearest integer to the real result. Now, the constant can be defined in various ways, as a float or fraction value, or as a reciprocal to perform a divide operation. It may be useful at this point to look at how the compiler processes this expression, to see why it is processed considerably faster than the equivalent floating point expression. First, the preprocessor performs string replacement, which expands the macro and substitutes the specified parameters into the expression. The sub-expression shown in red is calculated by the compiler using floating point operators, and then converts the intermediate floating point results into a type-long integer literal constant. The compiler generates machine code instructions that perform a type-long integer multiplication, then a type-long integer addition. Then it shifts the value right by 16 places, leaving the result in the lower 16 bits of the 32-bit register, which it then assigns to variable ans. If this expression were to be entered as a statement instead of the macro expression, the runtime machine code generated by the compiler would be exactly the same. The integer expression works by the compiler converting the specified constant into an integer fraction, which has a denominator value of 65536. Each step increase of the integer numerator value increases the value of the fraction by 1.53 e to the minus 5. In other words, the fraction value has a fixed resolution equal to 1 over the denominator. If the constant cannot be exactly represented by a fraction, there will be an error introduced. The maximum error introduced by representing the constant as a fraction with a denominator of 65536 occurs when the constant value lies midway between two consecutive fractions. This is when the error is equal to half the resolution of the fraction, which is 7.6 e to the minus 6. In addition to the constant conversion error, there is also the integer rounding error, which occurs when the result is rounded to the nearest integer. This can introduce an error of up to 0.5 compared to the real result. So the maximum error produced by the integer expression is a combination of the constant conversion error and the integer rounding error. The largest error that will occur for a particular application depends upon the value of the constant and the maximum value of the variable. However, the largest error may not necessarily occur at Vmax. It will probably occur at a lower value. This is because the constant conversion error only manifests itself when the fraction result and the true result straddle either side of a 0.5 boundary. The value of the variable at which the maximum error occurs is not easy to calculate mathematically, but can be obtained by running a small test program that loops through the full range of the variable. This example shows the constant pi. The largest integer rounding error occurs when the variable has a value of 8712, because this is when the fraction result and the true result straddle either side of the midway point between two integers. The flexibility of the integer expression can be increased further by including a second constant which performs the operation v times c1 plus c2. If the second constant is not required, it just needs to be set to 0. This is the final version of the integer expression. So, just how much faster is this integer expression macro? Well, I ran several tests using the MPLAB X simulator and XC16 compiler and found it to be on average about 25 times faster than the equivalent floating point expression. So you may want to consider using it when execution speed is a priority. The integer expression macro is only of use when the constants are literal or symbolic. It will perform slower than a floating point expression if the constants are defined in a variable, even if it contains the const qualifier. Also, there is no point using the macro if the constants are integer values, because the compiler would use integer operations anyway. The integer expression macro shown here is for general purpose use. It accepts signed parameters and produces a result in the type int range. But there are many variants of the integer expression that can be created. Here are a few of them. This is an unsigned variant and can produce a result in the range 0 to 65535. This uses a type long integer and converts the constant to a fraction with a denominator of 2 to the power 32. The range of the result is greater, but the use of type long integer operations is slower, so this variant is only 5 times faster than a floating point expression. This variant provides flexibility in range and accuracy. A specified value of parameter s that is less than 16 allows a greater result range but with reduced accuracy. This is an interesting variant but probably of little practical use. I did this more as a theoretical exercise. It uses the largest possible denominator, which is calculated from the variable maximum and minimum values, which have to be specified when the macro is used. I have not shown how the expression is derived because I think it is a bit of an overkill for any practical use. Interestingly though, this expression is still 25 times faster than using floating point. It is difficult to state what the result range is, because the greater the range, the lower the denominator value in the constant to fraction conversion. Well, that concludes this video session. The objective was to create a general purpose integer expression macro that can be used to replace a floating point expression. So it just remains for me to say thank you for watching and goodbye.